1/2. Not exactly a celebrity in the world of numbers. But it is the most commonly used fraction, and it's unavoidable if you're looking for symmetry. Today we're gonna invite it on stage with a rather more famous champion of symmetry, the golden ratio, phi, and let the two of them tell us a bit about their secret relationship. Stay tuned. In the previous two videos in this series, I've been leading up to this story. You can find the playlist in the description if you feel like you need an introduction to the golden ratio, as I'm only going to do a quick recap here. The golden ratio, phi, is a special proportion that lets you relate individual parts of a shape to its whole. It has an interesting internal structure containing its own inverse and 1, and writing it in its exact form reveals 1/2 inside of it. In the last video, I took the two versions of phi we got from its defining quadratic equation, -1/phi and phi itself, and drew them on a 2D coordinate system with the number 1 standing orthogonal to them on the vertical axis. I then took advantage of the fact that 1/2 stands right in the middle between those two versions of phi to show how the remaining square root of 5/2 connects all the points we've defined. This works as a sort of anatomy chart of phi, helping us investigate it further. The most obvious shapes we can identify here are the two golden ratio rectangles, a smaller one here and a bigger one here. This shape is quite famous and used as a basis for much of golden ratio geometry, but I'm just gonna go ahead and cut it in half. Not down the middle, not across, but diagonally. I spent a lot of time looking for references to this type of triangle so I could call it by its proper name, but to my surprise, my search turned out blank. It's definitely not called a golden triangle, that name belongs to a different one. So I'm gonna give it a name. Let's see if I get corrected or it catches on. Let it be known as the golden semi, and its definition be simply the right angle triangle obtained by cutting a golden rectangle along its diagonal. The golden semi also appears on our chart to the left of the vertical axis here. Remember, these three sides are all connected by a factor of phi. This is 1/phi, multiply it by phi and get 1, multiply that 1 by phi and get phi. Let's do a similar thing with 1/2, represented by a half square here. We're going to cut it diagonally and get another right angle triangle, this time with a ratio of sides 1/2 to 1, or simpler 1 to 2. At first glance, the green golden semis and the new purple triangle aren't related to each other than both being right angle triangles. But if we pay attention to the semicircle drawn around them, we notice that these two lengths are both its radius. So they are the same. With this side, they complete a new isosceles triangle, that is, a triangle with two sides of the same length. And it's this Frankenstein mix of angles and sides of the green and purple triangles that's going to help us find the link between them. I know it looks like all three sides of this triangle are the same, but they're not. Let's sidebar for a moment to remember a couple of properties of triangles that are gonna come in handy here. First, when we have a right angle triangle and we're only interested in its shape, not its scale or orientation, we can fully define it using only one angle. That's because all angles in a triangle must add up to 180 degrees, and one of them is already set to 90 degrees, so when you fix one angle, the last one remaining is just 90 degrees minus whatever you chose. Second, an isosceles triangle is just two of the same kind of right angle triangles in disguise. So these two angles must be the same. Okay, armed with this knowledge, we can first pick a defining angle for our green and purple triangle types. We'll use alpha for the green one and beta for the purple one, in both cases picking the smaller of the two. Then, we look at the isosceles here and see that it shows us that these two angles have to be the same. Okay, this one we know to be 90 degrees minus alpha because it sits across from alpha. And the one up here is alpha plus beta. So 90 degrees minus alpha is the same as alpha plus beta. Let me go ahead and replace the 90 degrees minus alpha with alpha plus beta down here. Coming back to our equality up here, If we leave the right angle, 90 degrees, on the left, and collect our defining angles on the right, that gives us 90 degrees equals 2 alpha plus beta. But since this whole corner up here is made from the two opposing angles of our green triangle, we know that's a right angle, 90 degrees, so we find out that it's made from two copies of alpha, cradling a beta exactly in the middle. And what about the opposing angle of the purple triangle? We can write it first as 90 degrees minus beta. Then we take that, replace the 90 degrees with the 2 alpha plus beta we found before, the betas cancel out, and we're left with just 2 alpha. Let's replace that in the triangle too. Now, all the angles present in this picture can be written using only alpha and beta, the two defining angles of our two triangle types. This relationship of angles, however, isn't specific to 1/2 and phi. We could replace those two with other numbers and still get the same thing going on. I've left a link in the description to this Desmos graph that lets you play around with it if you're curious about what makes it work. But there is something special about this particular choice. It's the sweet spot where we get the 2-to-1 relationship both in the domain of side lengths and the domain of angles, and all of this happens around a unit square. We see another layer of symmetry hidden in the golden ratio, extending directly out from the most basic shape we can draw in 2 dimensions. And we're not done yet. By completing the circle and the rectangles and drawing them on a grid, we get several levels of 2-to-1 and phi aligned with grid lines for easy reading. If we play around with orientations, we can even find things like half of phi or half of phi to the -2nd power. Once again, you can do everything I am doing in Desmos. Links in the description. If you think about it, it makes a lot of sense these two ratios would be so intimately connected. The golden ratio is essentially a constant of balance between two connected but opposing tendencies, and 1/2 is a trivial form of the same thing. And just like the number 2 lets us do many useful things when we raise it to different integer powers, so does phi. In future videos in this series, we'll explore some surprising properties that arise when we do that, a sort of straddling of the line between addition and multiplication, so please subscribe if you'd like to see them. Until then, I'd like to hear about your experience in the comments. Feel free to post variations on the Desmos graphs I linked. YouTube doesn't allow links in viewer comments, but you can use the hash from the end of the link and people can splice it together with the rest like this. I'm curious to see what you come up with. Thanks for watching. I hope you enjoyed and learned something new. Bye!